purpose of this talk is to give a brief introduction to hyperbolic geometry and to pretty much discuss the research project that I did last semester. Right, so essentially we met up for the first day of the research class, and the goal was to create a right-angled hexagon, right? So, and this is what it looks like, pretty much. Right, so in Euclidean geometry, when you think of a polygon that is just all right angles, you think of a rectangle, right? So using a Euclidean sheet of paper, right, so you just fold over, fold, right angle, fold again, other right angle, fold, you get a right angle, and well, so now you get 4 right angles, you have your rectangle, right? So, and now here we have what I call hyperbolic paper, right? So the way I made this paper is that I begin with a circle of radius 3, right? So I did this in inches, so you have 3 inches here, and then another circle of radius 2, right? So and then I divided this up into 120 degrees, right? So into 3, really. And then I'll grab this piece right here, right? So I cut up these pieces around these edges and did that same thing for all the pieces, right? So I made like a bunch of photocopies for this, and then I'll just come and grab this piece and glue it to that, right? And then just keep going, right? Adding more and more pieces. And I had to cut little slits here because this part, the curvature of this circle right here doesn't fit perfectly onto here, right? So then I just kept this going until pretty much I got tired of making it, and now we have hyperbolic paper, right? So this is my attempt at making a rectangle in hyperbolic geometry, right? And this should essentially work the same way as the Euclidean paper, right? So fold a straight line, and then you fold it again, and so you get a right angle here, right? So you get this line, so just folding into straight lines. And you fold it again, you get a right angle, fold it again, right? But see what happens is once you get this third right angle, the last angle will end up being a cube. So I'm not sure if you can see this from far away, but to draw a picture of it, it just looks like that. So we have something like that, where this is a right angle, that's a right angle, that's a right angle, and then this is an acute angle, right? So this is called the Lambert quadrilateral. Right, so we'll find out that in hyperbolic geometry you actually can't have rectangles, right? So the best you can do is you have 3 right angles, and then the very last one will always be a cube. Okay. Right, so some history. So the discovery of hyperbolic geometry is credited to, and I will do my best to pronounce these names. So I think it's Janos Bolyai, Nikolai Lobachevsky, and Carl Friedrich Gauss. Right, so the main difference between Euclidean geometry and hyperbolic geometry is that it satisfies the first 4 postulates of Euclid's geometry, but then it doesn't satisfy the 5th one, which is also referred to as a parallel postulate. So really, what that says is that given a line L and a point P, not on L, there exists one and only one line through P that is parallel to L, or that does not intersect with L. Right, so then we have this hyperbolic axiom, which is pretty much a negation of this parallel postulate, which says that given a line L and a point P not on L, there exists at least 2 lines through this point P, right, that do not intersect with L. Right, and then the generalization is there doesn't only exist a line L and a point P, so that there exists at least 2 lines through P that do not intersect with L, but it's like for every hyperbolic line L and every point P, there exists at least 2 lines through P that do not intersect with L.
And are those lines parallel to L? In some sense?
Yes, so do not intersect parallel, right? So, and well, these are hyperbolic lines, and we'll get to that later. Right, so these are some models of hyperbolic geometry. Not all the models, but just three of them, right? So you have the Klein-List model, the conformal-List model, and the upper half plane, right? So I haven't worked with the first two, and I just chose to stay within the last one, which is the upper half plane, right? So I'll probably refer to it throughout the talk as just H2, right? So, and here is what the upper half plane looks like, right? These are just two examples of what lines will look like in the upper half plane, right? So they're not chosen there for any specific reason, they're just examples of what lines will look like, right? So we have that in the upper half plane, the points and the lines. So I will talk about the points, the lines, and then how length is measured, right? So the points look like, right, so we want x and y and R2, right, such that y is strictly greater than 0. Right, so we want everything except the points on the x-axis. And then for the lines, we want x, y, in the H2, right? And the lines look like x minus h squared plus y squared is equal to r squared, or x is equal to c, where h, r, and c are real numbers, and r is greater than 0. Right, so really we want vertical lines, and then we want semicircles that are centered on the x-axis.
That green is pretty hard to read from back here.
Oh, it's
Just
green,
a bit.
okay, so
I mean,
I'll
I
just
know-
use black. Yeah,
just
sorry
kinda-
about that, but
I can read it, but
okay,
the bottom.
all right, I'll just use black. But yeah.
Circles are not hyperbolas.
No, so like, no, semicircles centered on the x-axis in H2. Right, so here are some properties of hyperbolic geometry, right? So we have that the angle between two intersecting hyperbolic lines is the angle between the Euclidean tangent lines. So the Euclidean measure of the angle between the Euclidean tangent lines at the point of intersection. Right, so what this really means is that given two hyperbolic lines, right, so we have, let's say, this and that one, we know that the angle of theta in between them is the angle between the two tangent lines, right? So to these two lines, to these two circles at the point of intersection, right? So theta would be that Euclidean angle, right? And so another property is that all triangles have angles sum less than 180 degrees, right? So I will not go through the proof of this because it will take a bit of time. So if you want to look at it, just, I guess, come talk to me after the talk, right? So I'll just ask that you believe me. All triangles really do have angles sum of 180 degrees, right? So, and then you have that one, and there are no rectangles, right? So then we come back to this lemma quadrilateral. And the idea is, just like in Euclidean geometry, you can always divide rectangles into two triangles, right? So if you have two triangles, each of which has angles sum less than 180, then get that the quadrilateral will have an angle sum of less than 360 degrees, right? So you'll never get a rectangle. Right. So now here's the theorem. So the tangent line to a circle at a point P is perpendicular to the radius of the circle at that point. And the reason why I use the theorem is because it's going to be very important in our actual construction of that right hexagon that I showed you at the beginning. Right, so I'm going to go ahead and prove that. So the proof is actually pretty simple. So I'll do that right now. Right, so I'm going to do it in the special case that we have a circle of radius r centered in the origin. Right, so we want something in the form x squared plus y squared is equal to r squared. So this, right? So and given this circle, right? So we have this circle of radius r, right? So a point on this circle, right? So that would just look like x, y, right? So if you were to draw the radius right here, then you know that the slope of this line is just y over x, right? So we just want to show that the slope of the tangent line at that point would just be the negative reciprocal of that line.
Are these standard Euclidean lines you're talking about? Tangent lines?
Yes, because remember that we want essentially when we're constructing hyperbolic polygons, we want the angle in between Euclidean lines, right?
It's just you all of a sudden say tangent line, and now I'm getting really suspicious that line means which geometry's
Okay,
line.
so yeah, I mean the Euclidean tangent
Okay.
line, yeah, of the circle, but yeah, right, so that's what I mean, sorry
High
about
school
that.
famous result, got it.
Yeah, definitely. So this is Euclidean geometry, right? Okay, so we have x squared plus y squared is equal to r squared, right? So we'll just take the derivative, right? So we implicit differentiation, right? So we get 2x plus 2y dy dx is equal to 0, right? So we want to solve for dy dx. We get that negative 2x is equal to 2y dy dx, right? So dy dx is just equal to negative x over y, right? Which is just equal to negative 1 over y over x, right? So negative reciprocal of the slope of that one, which was just y over x, right? So the end. Right. So then before we talk about angles and hyperbolic geometry, I just have a question for you. So which one, I mean, before we talk about area, sorry. So which of these two polygons do you think has the larger area? Just
One on the right or
the one on the right. So you think the right hexagon has a larger area than?
you mean in the Euclidean plane, like as they are?
Oh, so we're talking about hyperbolic geometry, right? So you don't know anything about the area just yet, but just if you were to look at this, what would you think?
Right.
So you guys think it's the right one, right? Okay, well, actually, this was a true question because we have the exact same area, right? So, and to show you that, I guess I have to define what area is. Right, so area of a hyperbolic polygon is given by, so you have area is equal to pi over 180 degrees times the defect, right? So, and then I will define what defect is, right? So defect, right, so defect is, so the defect of a polygon is the difference between its angle, right, so I'll shorthand between its angle, sum, and the angle sum of the angle sum for Euclidean polygon with the same number of sides. Okay, so this is the defect. Okay, so the difference between its angle sum and the angle sum for Euclidean polygon with the same number of sides, right? So really this formula is given. So for triangles, we have that this is equal to, right, so triangles, we have that's 180 degrees minus the angle sum of the triangle. And then for polygons with, so for polygons with n sides, we get that that's just n minus 2 times 180 degrees minus angle sum. So then you probably recognize this from Euclidean geometry that this is the sum of the angles of the polygon with n sides, and of course this is the sum of the angles of the Euclidean triangle. Right, so going back to that, we have that the first one, actually that's called an ideal triangle, right? So to figure out the angle sum for that one, we just have to figure out essentially what each of the three angles is, right? So if we go on this, we have a circle of radius 2, and then we have two smaller circles of radius 1. right? So remember that the angle is the Euclidean measure between the Euclidean tangent rays, right? So at this point right here, the tangent line to this line, the tangent line to this line, or to this semicircle, would just be the vertical line. X is equal to 2. Does that make sense why that is? Right?
Yeah.
So the circles are tangent to the x-axis, right? So the tangent line would just be the vertical line x is equal to 2, right? But coming to this smaller semicircle, you get the same result. It's the same line, right? So essentially the angle between these two lines, or these two semicircles, is just 0 degrees, right? So you come here, do the same thing, and you get the tangent line to this semicircle at this point would just be the y-axis, right? So the line x is equal to 0, and then, between the tangent line to this one is also x is equal to 0, right? So you get another 0 degrees, and then same thing here, at x is equal to -2, that will be the tangent line, and then you get 0 degrees. So really, this triangle is the angle sum 0 degrees. So in hyperbolic geometry, you can really get a triangle whose angle sum to 0 degrees, right? So to find its area, you would come here, right? So you say pi over 180 times defect, right? So defect would be 180 degrees minus angle sum, which would be 0 in this case. Right, so you say 180 minus 0, 180 times pi over 180 pi, right? So this has area pi. And then using this other formula right here, right? So you come to our right angle hexagon, and that one has angle sum 540, right? So it has 6 right angles, right? So 90 times 6, you get 540. Right, so the formula, you come, and so that would be n would be 6, the number of sides, so you get 6 minus 2 times 180 degrees, and then minus 540 degrees. Right, so you get 720 minus 540, and you get 180 degrees. Right, so take that, multiply by pi over 180 degrees, you get that the area of the right angle hexagon is also pi. So all right angle hexagons will have an area of pi, and all ideal triangles will have an angle of pi. And so those two things have the same area. And so now I'll take you through a few steps on how I actually came up with this right angle hexagon I've been showing and talking about. Right, so, and also I will write down the steps for finding a hyperbolic tangent line. So finding a tangent line to another hyperbolic line, right? So step 1, you want to find the slope of the radius of the given circle. So find slope of radius of the given circle. Right, so in my case, I started with the circle that you see there, so the larger circle of radius 6, right, so the one in the middle, the one that's centered at the origin, right, but I'm just gonna call its radius capital R. And so I had this, and I started with a circle of a radius capital R. So I picked a point, right, so draw the radius, and then I just find the slope of the radius, right, so we know 2 points on the line to find the slope. And then the second step is we want to find an equation of the tangent line which is perpendicular to that radius. So find a tangent line, and remember the result that I proved, know that this tangent line will be perpendicular to that radius, right? So the idea is that it will go through the center of this perpendicular line that we're trying to find, right? So the next step you want to do is you want to find the x-intercept of that line to figure out where the center of this new line that you're trying to come up with is, right? So find x-intercept. Right, so once you find the x-intercept, you know what that point is, you know that point, so you can just use the distance formula and that you get the radius of this circle, and you know that it's centered at some point, we'll call it A. Right, so then you can draw this circle with that radius centered at A comma 0. Does that make sense? Right, so and then you know this is a right angle in between the circle. Right, so the reason why I started with a circle centered at the origin is that I wanted to take advantage of the symmetry of circles so that I'll have to essentially do half the work, right? Because given a point x naught here, right, you can find the slope here. Once you come and find the point negative x naught, the tangent line at that point will just be negative of that, right? So really once you draw that tangent line, it will just go through the point negative A, right? And then this circle will have the same radius as that one, but it will just be centered at negative A comma 0, while this one is centered at A comma 0, right? So really I just found two lines that are tangent to this first one. Right, and then I did the same thing again for the next one, right? So I just came to this circle, you know, find the tangent line, find the x-intercept, right? Went through this other circle, right? So then I drew that, and then I called the center of that one B, right? So I'm gonna call this the radius of this circle RA, right? And then the radius of this circle RB, centered at B, right? So then same type of thing here. You get that, right? So a circle of also radius RB centered at negative B this time. So is
Now is B the x-intercept of?
Right,
what
so
is B?
this-
Sorry.
so B is the x-intercept of the tangent line to this semicircle, right? So this is
At what
essentially
point?
so
Yeah,
this.
which tangent?
Okay, so coming to this semicircle right here, right? So let's call this semicircle capital A, right? So I came at capital A, right? So chose a point, right? Find
Oh,
the
just
tangent.
anyone you like. Okay.
Yeah, right. So here I was just kind of choosing points and just going through it.
The points you're taking are ultimately the vertices of the hexagon, the ones you're marking.
Yes, exactly, right. So you have here and you have here so far, and that and that, right? So yeah, so came here, found the tangent line, and then you know that it goes through the center of this new circle that we're looking for, so I just call that point B, right? So really it will be B comma 0, right? A comma 0. Right, and so here then you'll have that this right here is negative B comma 0, this would be A comma 0. Right, so these are the centers of these circles. Right, so then once you get to this point right here, well, we already have all these sides, and all we're missing is one more side, this hexagon, right? So we want to find this circle that's perpendicular to both of these, right, at the same time. Right, but then remember that it's centered at the origin, right? So we can break this up into a right triangle, and the way we can do that is, right? So I will just redraw these two and that one, so you can see more clearly. Right, so we have these two circles that we already have, right, with radius. So I'll call this radius RB. Right, so we have a radius RB. This one is centered at negative B0, and this one is centered at B0. Right, so we have these two, and we want to find this one that makes a 90-degree angle with that one and that one. Right, so essentially it just depends on the fact that you just need to find what the radius of this last circle is, right? Because we already know that it's centered at the origin, we just need to find its radius. Right, but knowing the radius of this circle right here, right? So that's RB, right? And then this x coordinate is B, you know that the length of this side is B, right? And then this segment is RB, this is the right angle, and then this is the radius that we're looking for, R naught. Right, so you can just, so we can say R naught is equal to B squared plus RB squared. I'm sorry, other way around. So it'll be B squared is equal to R naught squared plus RB squared. Right, so R naught would just be B squared minus, well, the square root of B squared minus RB squared. Right, and we already know what RB is. At this point, we already know what B squared is. So you can just find R naught that way. Right, so now we have all these. So that's the picture that you get to the left. So that's the work that went into doing this. So it was not really difficult. It was just very tedious, just time consuming, right? So, and then to get rid of all these, I had to figure out what essentially the points of intersection were. Well, I already knew what these points of intersection were, right? So I'm just gonna show the example of, let's say I just want to get this part of this semicircle right here, right? So this was a matter of me, right? So I will draw this. This is our circle with radius r, and if anything is unclear, please let me know. Right, so I'm drawing this semicircle of radius capital R, so that's the large one, center of the origin, right? And then I know this circle right here, centered at A, with radius RA. Right, and I wanted to figure out how to get just this part of the hexagon. Right, so I just drew a right triangle. Right, so I know this is capital R, right, and since I knew the point of intersection, I knew what this x coordinate was, and I know what this y coordinate was, right, so the angle theta here would just be theta is equal to R10 of y over x, right, and then, so this angle on this other side would just be pi minus R10 of y over x. Does that make sense? So,
what do these angles do?
so essentially it was, how did I go from left picture to right picture? So it was me going to each side of the right hexagon and trying to figure out what it took to just get the hexagon, not the extra, all the stuff that it took to get there. Right, so I just wanted to get this part of this picture. Right, so first step was me just going through each section, so each side, and trying to figure out just what the angles were so that I could get that picture. Right, so what I did here was just to get that part, and I did that for every arc, so every side of the hexagon separately, and then
So
I
plotting
combined
the arcs in polar form.
Yes.
Okay.
So yeah, so I was trying. So I would say on mathematics, I would say plot r cosine of theta and r sine of theta, and let theta go from r10 of y over x to pi minus r10 of y over x, and then I would just get that part. And I did that for everything. Yes.
So why can we have no rectangles in H2, but you can have right-angled hexagons?
Okay, so it all comes down again to like breaking it up into triangles, right? So remember, if the sum of the triangle is less than right, so if the sum of the triangle is less than 180 degrees, you will never have you will never have a rectangle, right? But when you have a hexagon, right? So it definitely allows for you to be able to divide it up into more than just two triangles.
Right,
Does
does it divide up into 4, I guess?
Right, so you have, so I guess that would work the same as in Euclidean geometry.
So the shape with all right angles have to be a hexagon.
No, right, so we'll find out that you can actually get right angle pentagons as well. Right, so my goal was create this right angle hexagon. Right, but you can get a right angle pentagon, you just can't get anything lower than that. So you can get a right angled, a right angle quadrilateral. So you can get a rectangle, but you can't get a right angle pentagon. And as you can see, you can get a right angle hexagon too. And a heptagon, octagon, and so on. Right, so we have this, and now I was trying to figure out a way to print this. Right, so then that's when we have the pseudosphere, right? So a visual way of explaining this is we wanted to take a portion of the hyperbolic plane, right? So take a portion of the hyperbolic plane, right? So in Euclidean geometry, when you take a, let's say this is a portion of the Euclidean plane, right? And then you fold it over, you get this cylinder form, right? So when you take a portion of the hyperbolic plane, you get this hyperbolic cylinder, which is what you see there. So that's what that looks like, right? And so the motivation for why that looks like that is, again, going back to our hyperbolic plane. Remember that that was equal to, so the integral of, so you have dx squared plus dy squared over y. Right, so these are segments that are, well, in Euclidean geometry would have a length of 2 pi, right? So they're going from 0 to 2 pi. Right? But in hyperbolic geometry, they're actually not 2 pi, right? So at y is equal to 2, that segment will have a length of 2 pi over 2, right? Because we're dividing by y. Yes.
Where's the integral coming in? I'm sorry, I wasn't paying attention.
Okay, the integral, so this is just how length, so length
Oh,
of
our
the curve
thing.
C, yeah,
Okay,
is defined by this, right? Right, yeah, so I wrote this down at the beginning at some point, right? So this is how you measure length in hyperbolic geometry, right? And then the upper half space, right? So at y is equal to 2, this segment that looks like it's 2 pi long would actually be 2 pi over 2, right? And then at y is equal to 3, you get 2 pi over 3, and then at y is equal to 8, you get 2 pi over 8, so pi over 4, right? So these are the circles, right? So these are the circles that you see. So this segment right here corresponds to this circle. But these are the circumferences of the circles that you see on the pseudosphere, right? So the idea was we wanted to take a portion of the upper half space and then find a mapping from that portion of the upper half space to R3, right? So essentially we wanted the portion of y is greater or equal to 1 and x is between 0 and 2 pi, right? So we want to take this portion right here and find a mapping. So find a mapping from this portion here to something in R3, right? So that's when you get the pseudosphere. And then the vertical lines, I don't know if you can see that, but we have the vertical line x is equal to 0, right? From y is equal to 1 to y is equal to 9, that will be that curved line on the pseudosphere. Right, so you're getting all the vertical lines being those curved lines, and then all these horizontal lines, which are not hyperbolic lines, but these horizontal lines are the circumferences of the circles on the pseudosphere. Right, so the higher up you go, the shorter the distance gets. The lower you go, the greater it gets, because you're dividing by y. So really, the closer you get to y is equal to 0, the larger the distance. And yes.
So when we have like concentric like semicircles on the upper half plane, if they're all centered at the same point, are the circumference, that distance, they're going to be the same because of that dividing by y?
Wait, so what do you mean? Do you mean like something like?
So like the two sort of concentric circles on the image that you have to the right, on the board.
On the board,
Oh,
yeah.
yes. Oh, you're talking about like these two.
Right.
Yes.
If we're just looking at those two, are those both going to have like the same length because they are, I don't know, because of this dividing by y?
Okay, so no, these wouldn't have the same length just because you're dividing by y. Wait, so okay.
That's what he said, yeah.
Oh,
That's
wait.
his question.
Is the
she
question-
said these would not. You said that
Oh, I wasn't asking a leading question. I was asking a question I don't know the answer to.
So I'm just trying to
There's
understand
the
the question.
circle from negative R to R, and the sort of semicircle bit from negative A to A. Are those different lengths?
Oh, okay, so yeah, you're talking about this circle, right? So, okay. No, so they wouldn't have the same length. I mean, so you're dividing by y, but it depends. So it depends where at y you are. So if you're looking for y is equal to, let's say, 2, right? So you're looking at this point right here where y is equal to 2. So you want to find this length right here and that length right there, and they will not be the same. Right, so just because you're dividing by y doesn't mean that this length right here will be the same as this length right here at y is equal to 2.
So we can only speak about lengths of line segments when y is 0 is the complete line and it has no notion of is that
Yeah, so
there's I guess the entire semicircle is actually a complete line. So if we were to try and find out which line was longer, we wouldn't have any notion of length at the axis because we'd be dividing by 0.
oh, okay, so yes, so yeah, what you have to take into account is, right, so so the x-axis is not part of our geometry, right, so you can think of the x-axis as being infinitely far away, right, because you're dividing, you couldn't divide by 0 essentially, so the closer you get to the x-axis, right, the further away you get. Right, so infinity is sort of in the middle of your page, right? So infinity will be right here. You can never get close to here, and the closer you get to here, essentially the distance gets larger and larger because you're dividing by something that gets really smaller.
So that means there's no such thing as a complete circle centered around the origin?
No, complete circle, well, the lines are defined as just a semicircle, right? So
Okay.
you wouldn't have this because that would be part of the geometry.
Right, because you're on the half.
Right, upper half. So it's everything there except for the stuff on the x-axis and nothing below the x-axis. Right, so just everything above the x-axis. Right,
But so a semicircle is infinitely long.
right,
Okay.
right. So it just goes on. I mean, it looks like it's touching the x-axis, right? But really, since this is infinity, it just extends all the way to
Yeah.
infinity. Yes.
So is the accurate visualization of length the picture on the right there? Like if two things look
Right,
longer
exactly.
there?
So this is what it would look like in Euclidean geometry, but in hyperbolic geometry, if you would take just that portion and fold it over, that's what you get. So this is the accurate portrait
So
of
those two lines that look like they have the same length
do not.
do
Right.
not, that they clearly do not.
Yes, so that shows you that they clearly do not, and that one, so this is misleading because in Euclidean geometry you say, oh, they're all 2 pi long, right? But in hyperbolic geometry you find out that you always have to divide by y.
Is that made by, you said we cut out a segment like from 0 to 6 on the x-axis?
So, yeah, so if you want to find a mapping from 0 to 2 pi,
0 to 2
and
pi.
everything above and including y is equal to 1. So this portion right here, take that, fold it over, right? So instead of getting this cylinder like we do in Euclidean geometry, you get this hyperbolic cylinder, the pseudosphere.
And is the hyperbolic cylinder actually like infinitely, I don't know, like stretches out infinitely far? Or is it limited like we see it there?
Right, well, in this case, we chose purposely for y to just be greater or equal to 1, right? So,
Right, but if we allowed it to go lower, it would get bigger and bigger.
right. Right, so this was just how we chose to map it. And then taking the right angle hexagon and putting on the pseudosphere, you get this right here, right? So you can maybe count that you see there's one right angle, the second one, the third, a fourth, a fifth, and a sixth. But the fifth and the sixth overlap, right? And the reason for that is these 2 points right here actually, right, so the distance between these 2 points turns out to be 48 over 5, right, and that's greater than 2 pi, and since the pseudosphere is only taking into account the distance between 0 and 2 pi, it makes sense that it would overlap on the pseudosphere, right? So, and I have the actual hexagon on the pseudosphere here, if anyone wants to see it. Yes, you can pass it around. Right, and so mentioned earlier that you can have a right angle pentagon, right? So this was just me coming to the right angle hexagon, dividing into 2. So using the line x is equal to 0, and then just using this portion right here.
Is that a line?
Yes, because remember vertical lines and then semicircles centered on the x-axis. So it is actually, no, it's fine. So it's an actual hyperbolic line, so it's valid, right? So then you can see that you can actually get a right angle pentagon that does not overlap, right? Because it's just half of the right angle hexagon. right? So this is what it looks like. Wish I could have printed out one for you to see, but I do not have it. Right, and so I guess I will end by saying that I'm still trying to figure out a way to construct a right angle exciton that does not overlap on the pseudosphere. Right, so we have this restriction that we have it to be between 2 pi, right? So we want this point right here to be at the furthest negative pi, and then this point right here to be pi, right? So we want to essentially fit all this in 2 pi of space, and then we want all these intersections to be above y is equal to 1. Right, so I'll draw a better picture here.
In Euclidean geometry, you can just shrink stuff. Can you not do that here?
Yeah, you can shrink the polygon. So really that will come down to, so you can multiply all the radii by a factor of 2, and then multiply these centers by a factor of 2 as well, and that will shrink the whole hexagon.
But
Right.
it still overlaps because of the y.
No, okay, so
It doesn't.
So if you're thinking of me coming to this so coming here and then shrinking it to try to fit into 2 pi, well, what happens is when I shrink it, I can shrink it to fit between 2 pi, but then these points, so the lower points here go below 1. Right, so I have the restriction that I have to fit everything into a space of 2 pi, and then everything has to be above 1. But by shrinking everything, I can get it within 2 pi, but then I can't get it above 1. So I couldn't get it on the pseudosphere if I wanted to, right? So I'm still trying to figure out how to do it, but so that's really the last question, to figure out how to do that. Figure out how to get this point right here to be pi, and this negative pi, and then absolutely all the intersections between all the semicircles to be above the line y is equal to 1. And so the only thing I know for sure is that given that this is capital R, and that this has to be greater than 1, and this is pi, I want R to be greater than the square root of pi squared plus 1. Right, so I want R to be about 3.96, sorry, 3.2696. So all I know is that R has to be greater than that. How much greater, I don't know. So I created a notebook on Mathematica that just runs these numbers for me. Really, so I tried 3.3, run it, try to see if everything is above 1. But with the whole trial and error thing, I've only gotten as close to getting this last point of intersection to be about 0.8925. So I still haven't figured out if it is possible to get this hexagon, the pseudosphere, to be, to not overlap and then to be above 1. This is what I know, but it's really all I know. So I'm really now trying to prove that it can't be done because I can do it. But yeah, so yeah, that's pretty much it. So that was my project.
So is there a way to generalize this to like heptagons, octagons, and make more and more polygons to the right side?
Right, so I mean essentially you can do this as much as you want, right? So given, well, you don't have to use the same construction I did. I just used this semicircle center of origin just because it was easier to use symmetry. But I mean you can do as much as you want, right? So get all the right angles that you want.
Oh.
I mean, it's not guaranteed that they will be on the pseudosphere that we created because we don't know that all these intersections will be above 1, but you can create angons, however large you want, by just drawing circle and circle and making sure that the right angles between them. Yes.
But what do circles look like? Maybe in the half plane. Like, could you have? What does it look like to say the locus of all points equidistant from a single point using these segments?
Actually, do not know. So I'll admit that I've not thought about that. Because our hyperbolic distance is really different, right? So start given a point, trying to find all the points, like a certain distance away from it is very much different from plane geometry. So
Right.
I guess it's just something I can think about.
Yeah.
I think at least one, I don't know the general answer, but at least one class of circles are lines parallel to the x-axis. Just to flip things around.
Oh.
Euclidean lines parallel to the
Oh,
x-axis
That makes sense.
are equidistant from something. I'm not sure what.
They're not,
Huh?
they're not circles. So by circle you mean
Oh no, those
equidistant
aren't
from a
to
single
those.
point.
Yeah, no, I'm wrong.
Right, so yeah,
I'm wrong
given
about that,
a
yeah.
specific point, I guess all the
Those are
set of
orthogonal.
points that are,
So the theorem is actually that those are actually Euclidean circles.
Really?
Yeah, but the center is not a Euclidean
That's
center.
right.
Wow. Where's this?
So if you think of, here's a way to think of a circle. If you have top and bottom point of a circle, it's, as a Euclidean circle, the center is the average of those two, right? The arithmetic mean. As a hyperbolic circle, it's at the geometry.
Ah.
That's a statement that
are there any more questions?
All right, well, thank you guys for coming out. And please help me giving Amanda another round of applause.